You're listening to Electrician Live with your host, Paul Abernathy. Well, hey everybody, welcome to Electrician Live. My name is Paul Abernathy, your host as always, and welcome to the podcast. And all of those that are watching over on the video stream, what's up, what's up? So today's episode, as you've probably seen, if you visit electricianlive.com and actually look at the show update, you'll see that tonight's show is dealing with service bonding and kind of everything revolved around service bonding. So we're going to talk about that tonight, and I'm going to try to paint a picture for all of my folks that are over on the podcast, which again, we have way more listeners in our podcast streams than we do on our YouTube channel. So I'm encouraging you to come and visit our YouTube page, which is youtube.com/masterthenec. Hopefully you will check us out, give us a look, and watch some of the videos that we have. As well as, again, if you want anything on the 2020 code, you're not really going to find a whole lot of that over on our YouTube channel because we share that up on our Patreon channel. That's where our Patreon stuff is. Okay, so that's 22 dealing with the 2020 National Electrical Code. So that's where we're gonna be for all of that information. Okay. And so, well, anyway, welcome to the show tonight. So we kind of going to get into a presentation. So for a treat, the people that are over on the video that is streaming live, either from electricianlive.com website or from YouTube, will get to see kind of the presentation that I'll be talking about and when I go back and forth into the National Electrical Code. And for those that are listening over on the actual podcast, at any time after this show is produced, you can go watch the rebroadcast of tonight's show. And that way you'll be able to see comments. You'll be able to see any type of interaction that we have when it comes to the National Electrical Code and all that kind of stuff. So tonight's episode is obviously on Electrician Live. We're going to be talking a little bit of code, so got to buckle up for that. All right, so let's kind of go on and get started tonight. Again, we're going to be talking about the 2017 code because not a lot of people have migrated to the 2020 edition yet. And so as we get more people that actually come into the 2020 code, we'll start changing some of those presentations for Electrician Live dealing with 2020. Of course, we have other topics. Don't forget next week's episode, which we're going to actually have the top 3 residential and 6 commercial changes to the code. And I have a special guest. It is an interview, kind of a one-on-one with Jeffrey Mort. Who's with 3-Phase Radio. So we'll be sharing that. So you'll be able to watch that. So that'll be a really good show next week as well. So make sure you save, bookmark, subscribe, do everything that you need to do in order to be able to make sure that you remember that we're going to be here next week as well. Same time, same channel, 8 p.m. Central Standard Time. So we're going to talk service bonding, service grounding, and of course, that means we're going to be dabbling in Article 250. Now, Article 250 is probably, without a doubt, my favorite article in the entire National Electrical Code. Not because I serve on Code Making Panel 5. That's a bonus. It is simply because the concepts of grounding and bonding, which is some people find very confusing, I find very gratifying when you start to really begin to understand it. When you get to that point where you realize that a ground rod can only handle so much. And so whether I take a 4/0 to it, or I take a 6 AWG copper, it's just okay. It's good enough. The ground rod can only handle so much anyway, right? So once you start getting this epiphany of understanding the concepts of grounding and bonding, and it's kind of interesting. We had a discussion the other night in our exam prep, and of course I encourage you to join us during the week. Usually it's about Wednesday night or Thursday night, somewhere around there, maybe Friday night. Depends on how I feel. If you subscribe, you'll know when it's coming. And we'll usually do some exam prep, and I did a presentation. We had a great debate about grounding and bonding. And again, it was a really good interaction, and I enjoy those interactions where people can ask questions. So make sure you join us. If you're listening on the podcast, jump on over to our YouTube channel and subscribe. Okay, so we're going to talk some concepts here, main bonding jumpers and bonding at services. We're going to talk about all that. So we're going to look a little bit at some definitions tonight, talk about them for bonding and bonding jumpers. We're going to see the function of a main bonding jumper and a supply side bonding jumper and talk about those a little bit because those are very important. We're going to be sizing main and supply side bonding jumpers. So we're going to be talking about that so you kind of get a good idea of how you size them. Now, of course, you're doing through the podcast. It's not the same as seeing it on the screen. So bear with me as I try to convey that message to you. We're going to talk about bonding, the methods that you would bond at the service equipment. So you know we're going to be in 250.92. We're going to talk about the uses of grounded conductor, the neutral for bonding on the line side or supply side of the service disconnect. A very popular thing to do. Really is going to save you a lot of time and labor, and the code is okay with it, even though if you kind of cringe and think, wait a minute, you mean you're going to actually connect the neutral conductor to the actual enclosure on the supply side, let's say a wireway or whatnot? And the answer is absolutely. And we'll talk about that. And of course, we'll talk about the requirements for grounding and bonding at remote metering, which is very common. I used to do quite a few large homes who did not want the meter on their home, so it was kind of remote. It was kind of in a remote location and then everything like that. But again, it was just a meter. It's just a pass-through. It wasn't a service. And so again, you just pass through, but we had it remote just because they did not want it on the house. And those big mega homes, that we're familiar with doing. So that's how that came to be. Okay, main bonding jumpers and bonding at the service. So the main bonding jumper, which in many cases you run into for the electrician that's used to doing electrical panels, just basically in residential, things like that, they usually will supply a green screw. Okay, so if they supply that green screw, that is your main bonding jumper. No sizing required. You just use it. And that's going to be something that's placed in there. And what is its function? What is it doing? What is it? It's linking components together. It is linking the grounded service conductor, which is coming from the service. It's linking the equipment grounding conductors that are coming from the various branch circuits and feeder loads that are going out. And then, of course, you've got the grounding electrode conductor, which is going down to the grounding electrode. So the main bonding jumper links and connects all of these together, okay? And that's why it's so critical that we have it. Again, you'll hear me talk about the fact that, if you don't have a main bonding jumper and you have a ground fault and it gets over onto the equipment grounding conductor, it comes back to the service and it doesn't have a way to complete that system back to its source, which is back to the transformer via the grounded conductor, because of this mutual connection at that service equipment, then there's really no way to trip that overcurrent device. And you have to have that low impedance effective ground fault current path all the way back to be able to clear that overcurrent device. So if you get a situation where you notice that you're at a service and the main bonding jumper is not installed, then it's going to be really hard for those devices to function like they're intended to function, okay? So that's the main thing we cover is the main bonding jumper is kind of the melting point, the melding between the grounded service conductor that comes in, the equipment grounding conductors, and the grounding electrode conductors all at one common location within the equipment, service equipment, okay? Now, thinking about this main bonding jumper, its primary purpose of the main bonding jumper is to carry the ground fault current from the service enclosure and from the equipment grounding conductor system that is returning to the source during a ground fault condition. So if you think about that function, it's creating this. Now, when we think about electricity and whether or not we get into conventional electrical theory in the aspects of how things flow or how current flows, because we use the analogy that it flows like the water through a pipe. It's not really how it works, but if it helps us bridge this understanding together, then we'll kind of roll with it. But when you have a current that's going out into the system to supply the loads or whatever's happening here in this beautiful thing we call electricity, and there's a ground fault condition, so any of the ungrounded conductors come in contact with the grounded components, you create what's called a ground fault. And if you bond everything right, you connect everything right, and you have a low impedance effective ground fault current path that provides it to come back with low impedance back to the source, which is back to the transformer, then it's going to allow the clearing of an overcurrent protective device. Without that main bonding jumper installed, it gets there and it doesn't complete the system. And at that point, you just have live, potentially energized parts. In fact, not potentially, they will be in a ground fault condition. So that main bonding jumper is critical. Now, people ask me all the time, well, why don't I install it downstream of the main panel? Because the code won't let me, okay, under 250.24a5, that improper case to neutral. So I have to separate it and isolate the neutral away from the metal parts. But then I still have an equipment grounding conductor that has to bond or connect to the metal parts. But that neutral is isolated. The reason for that is if we were to take that neutral and use a main bonding jumper downstream, then what would happen is it would put return current, which is going to be on the neutral, flowing on metal parts. These metal parts are not supposed to carry current under normal conditions, only under ground fault conditions. So we know that current is technically always, especially in its typical normal branch circuit, it's always traveling on the grounded neutral conductor. Now, in a multi-wire branch circuit, you got to have a shared neutral and everything's balanced. You'll have zero traveling on the neutral. But when is that a reality? Okay, it might happen and it might not. So it's really the neutral is designed to carry the imbalance between the two phases. But that's in a perfect world, that would be the case. So there's always some current going to be traveling on the neutral. So if I make an improper connection downstream and accidentally, and we're going to say accidentally, as we hope it's accidentally, is that they take the neutral conductor and connect it to the case. That is a problem, okay? And we don't want that to happen because now you're going to energize metal parts that weren't intended to be energized. So that's why we separate it downstream, okay? Now, second thing we want to talk about, it ensures that the equipment grounding bus is at the same potential as the earth, where the grounding electric conductor is connected directly to the grounded service conductors. All of this, again, comes together at that bus. Now, I had an interesting question the other night when somebody said, now, don't you think we should change the equipment grounding conductor to the equipment bonding conductor? And this has been proposed for many years, and it keeps getting shot down. And I kind of gave this some thought. And I said, it does serve bonding, but its primary function also is to ground it and put everything at the same potential to earth. So if I were to rename equipment grounding conductors to equipment bonding conductors, it would not change its function, and it would be that we'd still have to have an informational note that explains that it serves multiple roles, because it does. So I think that the term equipment grounding conductor personally serves it fine. It is a grounding conductor. It is a bonding conductor. Now, I'm certainly not an advocate to call it equipment grounding / bonding conductor. No, I'm not going to go to that camp. But I think it's perfectly fine. But that's what it does. It brings everything. The main bonding jumper inside of the panel brings everything together. Now, the main bonding jumper completes the earth connection to the grounded neutral conductor, where the grounding electric conductor is connected to the equipment grounding bus as permitted in 250.24a4. Okay? So all of this kind of comes together inside of the service equipment. Now let's talk a little bit about some definitions. Okay? Bonded, which is bonding. So when I talk to people about these terminologies, and we have to understand these to understand service bonding or any other bonding within the scope of the National Electrical Code, most specifically Article 250, is that bonding is the act of doing it. Once it's done, the result is that they are bonded. Okay? So when we see the term bonded and you see bonding, just remember, tying all metal parts together is an act. We're tying it all together. It's something that we have to do. We have to follow the rules and the requirements and bond everything together, follow everything in 250.4, follow the rules. Once that is done, it is considered bonded. And what does that mean? The definition says connected to establish an electrical continuity and conductivity. So if I have two pieces of metal and I literally connect them together with a piece of wire, I am bonding them together. Once that is completed, they are now considered bonded. Okay? Now, main bonding jumper. And again, we're in the 2017 code. So 2020 code has some slight changes to different terminologies and things. But again, we're talking about the 17 in this edition. And if I get enough thumbs up and likes to this presentation and you share it with a bunch of people, maybe I'll come back and do one for 2020 and even show you the changes that took place within that. How about that? Usually I would save those for Patreon, but I will do that on another Electrician Live if you want that episode. People have been requesting a lot of bonding stuff, so I'm not sure why. All right, so a main bonding jumper, what is it? We've kind of described it, but now we have a definition for it. It's the connection between the grounded circuit conductor and the equipment grounded conductor at the service. It's that mutual joining that takes place within the service equipment, okay? And next is a supply side bonding jumper. Now, this definition is in 250.2, but in the 2020 code, it gets moved to Article 100. All right, but what is a supply side bonding jumper? Now, we know it's on the supply side, so a supply side bonding jumper is going to be something that we use to jumper. Let's say we have service equipment and we have an open bottom. And coming in through the open bottom, we have metal raceways. So now we have to bond to these raceways. So if it's supply conductors that are coming in, then we're going to make supply side bonding jumpers over to these raceways. And those are going to be supply side bonding jumpers. And we're going to size those in accordance with 250.102C. So we'll talk about that when we get there. But what are they? What are supply side bonding jumpers? And we'll see some graphics here in a minute for those that are over on the video. If you're over on the podcast, I will do my best to explain them to you. So what is a supply side bonding jumper? Well, the definition within the National Electrical Code is a conductor installed on the supply side of a service or within a service equipment enclosure or enclosures, or for a separately derived system that ensures the required electrical conductivity between metal parts required to be electrically connected. So that is the definition. So if I gave you another example of a supply side bonding jumper, other than what you're familiar with a service and all those raceways and that might be on the service supply side, how about from the secondary side of a transformer where we have secondary conductors that go up to a panel enclosure? Okay. That would be either it could be a fixed metal raceway would serve as a supply side bonding jumper, or we put one of the wire type in that goes from the secondary all the way up to the panel enclosure. That would be a supply side bonding jumper. It's being supplied from the secondary of a transformer. So that's a reason why it states in here separately derived systems. Transformers are separately derived systems. Now, not all transformers. Auto transformers, which is totally different. And if you go listen to our recent episode on Patreon and you become a subscriber, you'll hear me explain what an auto transformer is. But an auto transformer is not a separately derived system. A normal transformer like you and me, a delta, delta, Y, delta, whatever, that is a transformer. There's no physical connection between the primary to secondary. That is a separately derived system, okay? Now, the grounding and bonding is intimate, whether it's supply the primary to the secondary, but not the primary to secondary phase conductors. They are not in contact. They are separated, okay? Now, main bonding jumpers, enlisted equipment, can be used without calculating the size. Now, what we're talking about is the green screw that comes in a panel. Don't have to do anything with that, okay? I don't have to do anything as far as sizing it or anything like that. Not required to do that. And so I'm not going to go overboard and try to do that and make it complicated and somebody look at it and say, well, is that green screw sized properly? I'm not worried about it because it comes from the manufacturer. Now, if I choose to use a wire type main bonding jumper, then I'm going to have to size it. Okay, and we'll talk about that. But if it comes with the equipment, perfectly fine. And as you see here on the screen, we have dead front switchboards, motor control centers. For those that are listening on the podcast, I'll just describe them. Panel boards, power outlets, and anything that's furnished by the manufacturers. We have specific UL standards that are going to address this, and they usually will come. We're used as service equipment with a main bonding jumper, and it will be pre-sized. You don't have to do anything else to size it, okay? Now, again, different if you decide to do it of the wire type and do it yourself. But it's very different if it comes with the equipment. I don't want anybody trying to look at a green screw and say, can that handle the fault current? Don't do it. It's not worth the brain, not worth it, trust me. Okay, now let's look at what we're talking about here. So here's a panel, and you can see this here. And this is the allowance. For example, you see where you had the equipment grounding bus and it is connected to the grounded neutral bus and it's connected together. That is a main bonding jumper. Okay. Now, it could have just one bus and everything is on one bus, and that would be okay too. So it says for the grounded system, 250.24b requires an unspliced main bonding jumper to be used to connect the equipment grounding conductors and the service disconnect enclosure to the grounded conductor of the electrical system, which is what we're doing here. And for those that are listening on the podcast, I'm literally showing a conductor that connects both the equipment grounding conductor terminal bus over to the grounded conductor terminal bus. Okay. And that connection between the two is the main bonding jumper. Now, of course, in this case, you see a green screw in the equipment grounding bus, which is actually making the intimate connection to the enclosure. Okay. Now, a lot of times there's one bus and it just has one green screw and you just put that green screw. But it doesn't always have to be a green screw, of course. It could be a Z bar. I call them a Z bar, a zinc coated bar that comes with the equipment as well. Just looks like a Z. So there's other methods other than just the green screw. Okay. Keep that in mind. Now it says the connection must be made within the enclosure for each service disconnect. Now that's important because I might have a group of maybe I come in and I have a CT cabinet, and we'll see a picture of this for those that are listening or watching over on the video. You'll see a CT cabinet, it'll come in, and then of course you go to a wireway, and then you've got maybe up to 6 service disconnects that's afforded to me by the National Electrical Code in 230.71. So let's say that I have that. Each one of those service disconnects are going to have a main bonding jumper, okay? And it might vary from manufacturer to manufacturer, but you're definitely going to have that, okay? All right. Now, this is the example I was just talking about. For those that are over on the video stream, and this is one of my graphics that I did back before I started using Corel Draw, so bear with me. I forgot to update these graphics on this one. Same premise, but you know the wires look kind of squared off and everything, but you get the point. So in this case, it's a CT cabinet, and it comes into a CT cabinet, and the CT cabinet is bonded, and of course, if you're looking at the video over on our YouTube channel, you'll notice that there's little green dots, and that green dot shows where it's connected to the enclosure. So interesting here, I haven't started to talk about it yet, but this is an example where on the supply side, I'm utilizing the grounded neutral conductor to bond my enclosure. And that is allowed to do that. So you see how I'm making that connection, okay? And that's 250.142 is going to allow me to do this. And so I've done it there. Now, of course, in this graphic, all of the nipples are PVC, so there's no need to bond those for simplicity. But at the end of the day, the main point here is to deal with the main bonding jumper. And so in this graphic, you'll see that this is the service disconnect, this is the service disconnect, and this is the main bonding jumper here. And it is connecting this enclosure to where you have equipment grounding conductors would go into here to the bus, the common bus, and it would be connected also to the grounded neutral conductor as well. Okay. You will notice, for those that are watching the videos, not the podcast folks, we have a wireway that's between the CT cabinet and the service disconnects. Again, we're using the neutral conductor to bond the actual metal wireway. And that is allowed in the National Electrical Code. And it saves me a lot of time and a lot of labor and a lot of mistakes that could be made if you don't know how to size bonding jumpers. Okay. So there you go. And we'll get into each one of these as we go, but that's your basic thing. Okay. So now there's allowance in the code. Remember, it says that every piece of equipment has to have a main bonding jumper. You remember it made that statement early on? Okay. Well, it says for grounded systems, an unspliced main bonding jumper is required to be connected to the equipment grounded conductors and the service disconnect enclosure to the grounded conductor within the electrical enclosure for each service disconnect. Well, what if I have a piece of equipment, say a piece of service gear, maybe it's a piece of switch gear, and I've got separate bays? Well, that equipment gets made up in a certain way, whereas when I have more than one service disconnect mean is located in an assembly that is listed for service equipment, and this one that we show on our screen it's 6 disconnects, it is service rated, okay? The code says An unspliced main bonding jumper is permitted to bond the grounded conductors to the assembly enclosure per section 250-24B, exception number 1. So in this case, rather than have to go into each individual enclosure where there's a service disconnect and actually make that connection to the grounded conductor over to the equipment grounded conductor, instead of doing that, this exception allows me, and we pretty much do this anyway for the manufacturers that make this large assembly equipment, actually has a common location where all the grounded conductors are terminated, and it has a main bus that actually has a main bonding jumper. And some of those come already factory installed, and it connects the grounded neutral to the equipment grounding bus bar. And that is your main bonding jumper. And if it comes from the manufacturer again, then you let them size it. You don't have to do anything with that. It's manufacturer driven. And a lot of this large assembly with multiple disconnects that each have their own enclosure, like a switchgear, this is what's going to happen because you're going to have one common location in this equipment where it makes all these connections from the grounded conductors over to for the equipment grounded conductors, and it allows them to intimately come together. And that is usually provided with the equipment and a certain specific location. Okay. And in this case here, you show, if you're watching on the videos, you have a bonding jumper that is factory installed. It is removable because, you could be using this piece of equipment downstream, not as service equipment. You could be using it as remote distribution equipment. And if that's the case, you would remove this bonding jumper, of course. But again, this is an example of one there. So again, if you're in the podcast, make sure you check out the stream later after it's uploaded so that you can see a picture of what we're talking about as far as a factory installed main bonding jumper. Okay. Here's another picture of one. So those on the podcast, it's basically just a Z-strap that is making a connection from the grounded neutral conductors over to the enclosure. And that is the main bonding jumper, and that is provided by the manufacturer. And it is perfectly sized, doesn't have to do anything additional to that. And then, of course, there's also our traditional green screws, and there's also our, what I call the Z bar, if you will, which is basically a bar that's kind of looks like a little Z, and it actually screws to the back of the enclosure, and then it fits into one of the actual holes of the bus. Okay, and that is acceptable as well. So that's the main bonding jumper. And of course, many times in residential, for those that are more familiar with the residential work, you're going to see that green screw inside of the panel. And that's what's going to make that intimate connection between the encase, the equipment grounded conductors, and the neutral conductors, and the grounded service conductor. All of that comes together on this common bus. And that is in the service. All right. And then lastly, for those that are over on the video stream, here's another type of bus designed in a system where it actually has a removable piece that is actually considered the main bonding jumper. Okay. All right. The functions of the main bonding jumper. It has three main functions. You've kind of heard me talk about it a little bit, but the importance of a main bonding jumper is it connects the grounded service conductors to the equipment grounding bus or conductor and the service enclosure. We've talked about it. Ties it all together. The second is that it provides a low impedance path for return ground fault current to the grounded service conductor by completing the ground fault circuit return path from the equipment grounding conductor and enclosure to the source via that service grounded neutral conductor that comes from the pole, okay, from the transformer. All right. So it makes that connection back to the source. Another thing to remember, current, when it comes to ground fault current, is never trying to get to the earth. It's always trying to get to the source. And we had a discussion the other night, like I said, just because I have a parking lot and I have light poles on parking lots, driving a ground rod there does not increase the safety of that circuit. In fact, it creates a hazard because it puts the systems at two different potentials. Okay. You have a potential there and you have a potential on that circuit. Now, if I'm working on that electrical system and it's connected to the earth, then I have a differences of potential, and that's how I create a hazard. And I'm not going to clear a breaker, so if I get locked in on it, I'm not going to be able to let go. If I have an equipment grounding conductor that runs all the way back to the panel, which ultimately is connected over to the grounded conductor back to the transformer, if there's a ground fault condition, I can rely, hopefully, on that overcurrent protective device to clear very quickly. And it's all about the time. That's what's important. Driving the ground rod at a pole on a parking lot is not required unless the engineer wants it, but that is totally different aspect of it. That does not connect it to any grounded conductor at the pole. That is just from the metal enclosure over to the earth. That's fine if you want to do it, but it's not a requirement by the code, okay? We just have to remember that we're trying to create these low impedance ground fault current paths to facilitate the operation of an overcurrent device. Clear that circuit very quickly so that we don't have energized metal parts. The main bonding jumper is so critical to the reliability of that. Now, it also connects the grounded service conductors to the grounding electroconductor, where the grounding electroconductor is terminated on the equipment grounding bus or bar when a wire type bonding jumper is used. Okay, so let's look at this graphic for those that are following. Here's our transformer. Here is the grounded conductor, which comes from our transformer down to our service. It connects to the neutral terminal bus. And then from that neutral terminal bus, I have a main bonding jumper that connects it to the enclosure. And then at that bus, I am coming down to whatever my grounding electrode system is, whatever it would be, ground rods, ground ring, plate, rod, concrete case, whatever it may be. And that completes my scheme of grounding and bonding at the service. Okay, so far, we're good. Now, I go downstream to a remote distribution panel. That's when I have to introduce a equipment grounding conductor. And once I get to that remote panel, you want to make sure that that equipment grounding conductor bus is intimate with the metal enclosure, but you want to make sure that the neutral bus is not intimate. It is actually floating. It's elevated from the metal components. Otherwise, we have circulating current that can get on the metal enclosures. We create objectionable currents, and it causes all kinds of problems in our system. It also can energize metal parts that weren't intended to be energized. It creates a safety concern. So a lot of the violations I see is downstream. People don't understand. And believe it or not, still on Instagram, still on these other networks, they literally still post pictures that they're very proud of. And here they've got a violation right in their face. And they're missing it. They're so proud of the work, but they miss the code. And the code is where we're going to save lives, not how pretty it looks. I'm just saying, things to think about. We want to always think about those things. All right, so again, this is where the grounding electroconductor and everything converge on one terminal bus. However, the code does allow me to do, if I use the wire type main bonding jumper, I'm allowed to have a separate equipment grounding terminal bus and a separate neutral grounded neutral bus, and I connect them together with a wire type main bonding jumper. And I am okay there. Now, in that rule, I am allowed to take my grounding electroconductor to the equipment terminal bus rather than directly to the neutral bus. Now, they all are acting as one, but I have an allowance here for me to be able to do it this way if I choose. Okay? So, again, just other ways to do things within the scheme of your grounding and bonding within your service equipment, okay? I think most of the time, people are going to have just one bus, or there are two buses on each side. They're connected together with a bar, and I think they're going to take everything to that bus. But there are other ways to do it that are allowed in the code for you to be able to do it this way. All right, so sizing a main bonding jumper. A main bonding jumper must carry the full ground fault current of the system back to the grounded service conductor, which, again, may be a neutral. Most of the residential stuff we deal with, it's going to be a neutral, okay? But it is always going to be a grounded conductor in a grounded system. So the neutral is just all relevant to its position to each phase conductor. So, again, that's how we do that. Now, size must relate to the rating of the service conductors which supply the service. So when I'm sizing this main bonding jumper, I'm going to do this based on these service conductors. That's what we're going to utilize. to do this. And the minimum size of the main bonding jumper is determined from the requirements of 250.28D. Okay. So let's kind of look it over now. So that's that. Now, and let's kind of go through the rules here. So here's the sizing of a main bonding jumper right here. And incidentally, I should say that 250.28D is going to ultimately kick you. It's going to kick you to 250.102C1, by the way. Okay. Just so you know that, because if you're wondering on the podcast how I jump, okay, from 250.28D and then I jump up to 250.102C1, it's because it's going to give you directions for sizing in 250.28D that's ultimately going to take you to 250.102C1. Now, depending on what code cycle you're in, 250.102C1 might be a totally new code table for you. If you're still back in the 2014 or the 2011 or something like that, you might be like, and I can't remember which cycle it actually came in, but this is a fairly new table. Because prior to this, we pulled everything from 250.66, which was really just for grounding electroconductors, but we utilized it for a lot of other things, even though that's not what it was really for, because we had to use notes to give us direction. Now they've been separated, and I was so glad to see 250.102C1 come into the code a couple cycles ago. Made so much more sense to keep it there. Again, we're talking bonding, so it's where it should be. All right, so those that are watching on the stream, we simplified this. I removed the meter so you don't get cluttered, and I'll try to paint a picture for those in the podcast. So you have a transformer. You've got your black, your red, and your white. Keep it simple. And it comes down through the meter and comes to our main disconnection means. And this one, we're going to utilize the ability to utilize a separate equipment grounding terminal bus as well as a grounded neutral bus, and we have a main bonding jumper that connects them two together. And we know that the equipment grounding bus is connected to the metal enclosure, so they're all intimately connected together. Okay, we could have done this on one bus, but the code does give us allowance to do this under this scheme that we have, which is a separate bus for the equipment grounding and a separate bus for the grounded neutral conductor. Okay, but they are intimate together. It's very important that we make that known. Now, in this case right here, as you can see in the picture, I defined, for those that are watching on the podcast, sizing of the main bonding jumper is based on the size of the largest ungrounded service entrance conductors. Okay, now size per table 250.102C1 and the table notes. So in this case here, if they were 500 kc mil coming in, I'm just going to use value. So I had two 500 kc mils coming in. What we're going to do is we're going to go to 250.102C1. So I am going to actually go to the NEC, and we're going to go to 250. And I'll scroll down for those that are watching. And I went too far very quickly right here. And we have 500 kc mil, and we'll say copper. So over 350 through 600, it's going to be a 1/0. And that is what's going to be our size of our main bonding jumper. That little jumper between the equipment grounding bus and the grounded neutral bus. Now remember, if it's a green screw, we didn't have to do all this. You with me? Okay. So interesting enough, you'll notice up here in table 250.102C1, and those that are in the podcast, I'll read them to you. This table is used for a lot of things. And remember, when we used to use 250.66 for all these things, that was really confusing because the title of it was grounding electroconductor. Yet the code was telling me to use it to size my main bonding jumper, my system bonding jumper, very confusing. Now it's much easier to comprehend. So 250.102C1 says you utilize this and this table subsequently for the grounded conductor, the main bonding jumper, the system bonding jumper, the supply side bonding jumper, and all that for alternating current systems. And the beauty of this is that you simply use the ungrounded conductors. Now, if you have parallels, so let's say I had two sets of 500, then I add them together, so 500, 500, and we only had one phase. You don't add all of them. You don't go A and B and A and B and add them up. No, it's just one phase you add them up. So if I have two sets of 500 kc mil, that's two phase A's or two leg A's or two leg, leg one, whatever you want to call it. That would be 500 plus 500. That is 1,000 kc mil. If that's the case, I come down here and I would go to over 600 through 1100, and that would be a 2/0 main bonding jumper. Okay. Now, the notes are important. Because if I happen to have a main bonding, ungrounded conductors that are coming in that are over 1100 kc mil copper or over 1750 aluminum, and again, we're talking parallels as well, because you're probably not going to get one that's 1100 copper by itself. I'm just saying. Probably not. Pretty sure you're not. You're going to get it in parallel if anything pushes up that value. So when it's at parallel, when you're over those values, then it can't be less than 12.5% of the area of the largest ungrounded conductors or equivalent in parallel. So again, if I had two sets of 500, that's 1,000 kc mil, not a problem. But if I had two sets of 600, then that is 1,200 kc mil. So my main bonding jumper couldn't be smaller than 12.5% of that 1,200 kc mil. You see how it sizes? Okay, so that's how we size it there. And let's get back to the PowerPoint for those that are watching in the video. Okay. And so that's how we achieved our size of the main bonding jumper that connects the ground and neutral bus to the equipment ground and conductor bus. Now, I can save myself a lot of grief. Just do this all on one bus and use the ground screw that comes with it. But if I want to do this and I want to separate it and I want to do this, then I'm going to have to size that main bonding jumper. Because remember, all of that potential fault current has to get back to that grounded conductor. And so that's why we're sizing that jumper that way, because we need to ensure that it's going to get back. And that's why we're using 250-102C1. All of this kind of works together. So let's do some examples here. So size this main bonding jumper. So I have 250 kc mil aluminum as my service conductors coming in. For those that are listening on the podcast, I've got 250 kc mil coming in. I go to table 250-102C1 if I'm going to size my main bonding jumper. If I need to size it, if it's not a factory installed product like the bar or the screw or whatever, I'm doing it with a wire, then I have to size it. Then I go to the table and it says that I need a minimum of 4 AWG copper or 2 AWG aluminum or copper clad aluminum to be utilized as my main bonding jumper. And yes, I can use copper or aluminum or even copper clad aluminum in this application. Just be careful which table you're pulling from, your copper or the aluminum, okay? So this is the table. People are looking at it on the video stream. This is the exact table that's in 250-102C1, and you can see where we're getting all the information from and how we're sizing everything, and also the relevance of the notes. That's important when we're dealing with over 1100 kc mil copper, over 1750 aluminum, okay? And there's where you see we pulled for that 4-aught 250 and or 4-aught aluminum or 250 aluminum or copper clad aluminum is going to require that. Now, here's another thing that people ask. Can I have a 4-aught aluminum but have a main bonding jumper that is copper? Absolutely. You just pull from here. It would be a 4, and that would be fine. Okay? All right, let's do another example. Now, this one kind of talks about the parallels. It is 3 500 kc mil coppers installed in parallel. So you're going to add the circular mills together. And if it's larger than 1100 kc mil or 1750 aluminum, we're going to use a 12.5% rule. So in this case, it's 3 500s. So that's 1500. So it's 3 times 500 kc mil is 1500. 1500 times 0.125, okay, which is the 12%. You have a calculator, you can do just 1500 times 12.5%, but you want to convert that. Then you start from the right side of the equation and move 2 spaces to the left. So it'd be 0.125, and that would be 187,500 circular mils. So I need a bonding jumper for that. So what I'm going to do is I've got to find a conductor that's going to give me 187,500 circular mils. So I'm going to go to Chapter 9, Table 8, and that's going to give me the circular mils of all of our conductors. And I find and pick a conductor that's at least 187,500. Can be more, but it's got to be at least that. And so I do that. That would be the next conductor that would exceed 187.5, puts me into the 4-aught conductor range. And that is 211,600. So obviously my 187,500 put me in an awkward position to go with the say a 3-aught. So I had to jump up to a 4-aught in order to be able to make sure that I cover that 187,500. Okay. It's got to at least be able to cover that 187,500. All right. Now this, the note again, we've already talked about the note, 12.5% rule, and that's what we applied. Okay. And we have a note 2 as well. And the note 2 kind of says, if the ungrounded supply conductors are larger than 1100 kc mil or 1750 kc mil aluminum, and if the ungrounded supply conductors and bonding jumper are of different materials, in other words, if we have the bonding jumper is one material and the ungrounded conductors are another material, basically it says the minimum size of the grounded conductor or bonding jumper, either or, shall be based on the assumed use of the ungrounded supply conductors of the same material as the grounded conductor or bonding jumper, and will have an ampacity equivalent to that of the installed ungrounded supply conductors. So again, the easy way to explain this is if I'm coming in, and I'm telling you right now, the easiest way to do this is to pull from the table, okay? Pull from the table. They're going to come out to be equate, all right? But that note is basically saying if I have copper ungrounded conductors and I have an aluminum main bonding jumper, I have to make sure that that aluminum main bonding jumper has the ability to carry the same amount of current that would be necessary as if it was a copper main bonding jumper for that size ungrounded conductor. So I just have to check and make sure. Most of the time we pull straight from this table, okay? All right. Now, let's move on to parallel services. Sizing the main bonding jumper, as you can see here, those that are watching on the stream, I have a picture of something that is no longer allowed in the 2020 code, but it is allowed in the 2017 code. And this is a big enclosure with 6 separate disconnects. And this meets the 6 disconnect rule. And so in this case right here, I have 3 sets of 500 kc mil, and I need to size my main bonding jumper. Okay, it's of the wire type, so I've got to size it. So what does the code say? If I visit 250.102C1, again, it says when they're parallels. So I'm going to take the 500 from each one of them like we did earlier, same example we just did. And I'm going to go and look up, and then I find that it's going to be 1,500. So that's over 1,100. Then I'm going to do 12.5%, and that's ultimately going to result in a 4/0. So that is what's going to be my main bonding jumper. Again, that's if it's of the wire type. It could be already installed from the manufacturer. Don't try to resize the bus bar, the Z strap. Don't get into that. Only if you end up doing something that requires you to install a wire type main bonding jumper that you have to start worrying about this, okay? All right, so supply side bonding jumper, we talked about it earlier. We don't need to rehash that. But what is the importance of a supply side bonding jumper? Why do we have it? Why are we bonding all these raceways on the supply side? Why are we doing this from the secondary of a transformer to the enclosure? Okay, from the secondary conductors of a transformer. Why are we doing all this? Well, the supply side bonding jumper provides electrical continuity between the source, which is the utility transformer, or in a separately derived system, it's from the transformer's XO and to that actual panel, which is kind of where you created a new source, even though it's not a utility. There's only one utility. It's not a service either, but it is basically secondary conductors that I hate to use the word derived, but they actually will originate from the secondary of that transformer up to the first enclosure. And in that case, we have a supply side bonding jumper in order to connect the two for electrical conductivity and continuity between the two. Okay, so that's what a supply side bonding jumper. Now, on the supply side, let's say service raceways that are coming in, well, they could be energized, and we have to be able to bond all that so that at least that energy gets back to the source. Now, whether or not it'll clear anything up there, we don't know, but it does keep everything at the same potential. But the code, more importantly, the code tells us we have to do it. So we do it, okay? We don't try to dig over it, we do it. So what does it do? It connects the bonding bushings where used to service grounded neutral conductors in service equipment enclosures. So if, again, I have raceways coming in and I need to bond them, there's stuff we have to do on services. And if they're concentric or eccentric or impaired knockouts, then we're going to have supply side bonding jumpers. And we got to know how to size them. Okay, so we'll look at all that here shortly. It carries the ground fault current from the ground fault that occurs on the supply side of the main overcurrent protection. Okay, so it carries any fault current that might happen there, and it provides a low impedance path for ground fault current back to the source. And I don't deal in utility, folks, but hopefully they have some provisions on the utility side that will help clear this if that becomes a case. Its supply side bonding jumpers can be non-flexible metal raceways or a wire type. So basic way I can explain this is if I have a transformer and I have a panel. If I run EMT, electrical metallic tubing, from point A on the transformer over to the actual panel, and that is called a non-flexible metal raceway. Okay, that's a fixed metal raceway. It can be used as a supply side bonding jumper, and no, I would not have to put a wire type supply side bonding jumper in the raceway. Wouldn't need to do it. I can utilize that raceway as it, but I can't do that with flexible metal raceways. I'm going to have to put a wire type supply side bonding jumper inside there. Okay, it's kind of an example of that. Now, service grounded conductors can sometimes also serve as a supply side bonding jumper. Absolutely, certainly can. And to be honest with you, we take the grounded conductor a lot of times and bond metal parts on the supply side. And the code allows this. Now, I have people say, well, if you do that, aren't you going to energize those metal parts? You have to understand that you put them all at the same potential, that beyond the fact that the code allows it, it is something that we can't remove. And so based on the way current flows and the way it's designed and the nature, it's a safe condition. And I don't want to go too deep into theory tonight because I don't have a lot of time, but it's okay. And at the end of the day, if you disagree with it, submit it to the code panel, but you're going to have to substantiate it because this is what we've been doing forever, okay, on the supply side. And the code permits it. All right. So how do we size supply side bonding jumpers? All right. So it's the line side of the service and the main bonding jumper. So it's on the line side. We're still going to size it based on 250-102C1. So that's going to be very easy for us. It's going to be based on the size of the ungrounded service entrant conductors. Very easy. We've already done that. We get how to do that. And we're going to use the rules in 250-102C. We got a C1 and we got a C2. Now, C1 is dealing with parallel conductors in the same raceway, and C2 is dealing with parallel conductors in separate raceways. So this ought to be pretty easy. We have two different ways to do this, and it could come either way, right? So here's an example right here. So for those that are in the podcast, you cannot see my screen, but I show an open bottom and switchboard where it comes in the bottom, and I have 4 raceways. And now I don't show the phase conductors here. I just show the grounded neutral conductor for simplicity's sake. And you have some options. And so in this case right here, I have 4 raceways coming in. So it's a parallel set that are coming in. All right. Now let's size it based on 250-102C2. And this is for sizing. Now I've got 2 options here. I could run what we call one single continuous loop through all of these raceways back to the grounded conductor terminal bus. Okay? I could do that. That is perfectly fine. But let's read what happens here. Okay? It says, where the ungrounded supply side conductors are installed in parallel in 2 or more raceways or cables, and a single supply side bonding jumper is chosen to bond all raceways and cables, the NEC required that the size of that SSBJ, that's supply side bonding jumper acronym, not be smaller than stated in 250.102C1 and table 250.102C1 and be selected, here's the kicker, be selected based on the total circular mill area of each ungrounded supply conductor in each raceway or cable. So if this raceway, all these raceways had parallel sets of 500 kc mill, then I am going to have to take, and I only take one phase. You don't add them all up, okay? So I take 500 phase A, 500 phase A in the second one, 500 phase A in the third one, 500 phase A in the fourth. Add them up, so that's 500, 500, 500, 500. And that is 2,000 kc mill, or 2 million circular mills. Wow. Okay. Then I've got to go to 250-102C1 because ultimately it kicks me back to C1, and then I select it from that table. That is huge. That means that wire is going to be massively large because we're going to have to do that, obviously, at 12.5%. So I'm just going to kind of do the math here. Times 0.125. And that requires a 250 kc mil supply side bonding jumper. And remember, this is all on the supply side. This is not the load side. This is supply side. This is service conductors in these raceways. So the problem with that is it's hard to find lugs that might accept a 250 kc mil. And that becomes a problem. But if I want to loop one through them all, and that's it, as long as I can find lugs that go onto bonding bushings that go onto these raceways, then I'm okay. If I can find it. Well, that's the problem. You have to be able to find it. Okay, so that brings me to the second method, which is the individual method. So in this one, it's slightly different because I'm only going to take account the conductors that are in each raceway. And so I'm going to run separate supply side bonding jumpers from that raceway, from that bushing, from that lug over to my grounded terminal bus. And that is dramatically going to reduce the size of my supply side bonding jumper. I do have multiple options, but at the end of the day, I need to make sure I have a lug that can work. And I need to make sure, again, cost of conductors and whatnot. I might have some of this wire laying around that works fine for this. So what would this be? So let's kind of look at it scenario. So in this case right here, it says everything is the same. But in this case, I'm using an individual supply side bonding jumper attached from the lug over to the lug on the bonding bushing for each raceway individually. And I calculate its size based on the conductors in that individual raceway. So let's say I have an ABC, 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 ABC. Again, obviously with the neutral, but they're not shown. The phase conductors aren't shown. Then I'm going to take phase A for that raceway. If it's 500 kc mil, that supply side bonding jumper is going to be based on that 500 kc mil. And I would go to 250 102 C1, and we will do that here. We'll go over to it, and that will be based on a 500 kc mil. And that would be a 1/0. And that would be my bonding jumper. Now, a supply side bonding jumper. That is dramatically more achievable than a 250 kc mil on a lug. Okay? I'm just saying. So, things to think about when you're doing your application. You have two different ways to do it in that application. All right? So, let me get back here. Okay. Now, parallel supply side bonding jumpers. Again, we kind of talked about it. It says parallel service entrance conductors installed in two or more raceways or cables along with supply side bonding jumpers require the supply side bonding jumper to be run in parallel as well. Okay, so again, in this scenario, I'm running it to each one. And it says sizing of the bonding jumper to each raceway is based upon the size of the service entrance conductors in the raceway. We did that, and that would be the same whether we're doing C1 and C2. Now, the reason we didn't do C1 is I will show you that for those that are listening or watching, it really isn't necessary because if you look at the application in just C1, you'll look and see that it says size of the supply conductors in a single raceway. The supply side bonding jumper shall not be smaller than specified in table 250.102 C1. So if I only have one raceway and I have black, red, blue and a neutral, and they're all 500 kc mil, I just base it on the phase A, and it's 500 kc mil. That's they're all the same size. I don't go 500, 500, and 500. Okay, that's a misconception that people do. No. It's only pick one phase and work with that one phase. Now, if I had a raceway that was large enough to have two phase A's, two phase B's, two phase C's, then I'm going to take the two A's, and if both of those happen to be 500 kc mil, considering raceway fill and everything was done, then that would be 1,000 kc mil, and I size it accordingly. So you see, it's not much difference. Okay, so it didn't think it was necessary to cover it because it's pretty straightforward in that application. All right. All right, so again, so that's what we're talking about. Now, in 250.102C2, we're also talking about what it says about parallel bonding jumpers where they're actually either in or outside of the actual raceway. In this case, using something like an FMC or a LFMC or LFNC, where I need to maintain the integrity of the raceway for this bonding, for supply side bonding. So here, you'll notice what it says in the code. It says bonding jumpers, such as supply side or equipment bonding jumpers, depending on how they're being utilized, okay, are also required to be installed in parallel and routed with the phase conductors that are installed in parallel in accordance with 250.102C2. Note that it is common to use, again, flexible, and for those that are in the podcast, you can't see it, but I've got raceways that come in and they have a transition fitting over to flexible metal conduit, and then that connects to the metal box, okay? And so in this case, we cannot rely on the flexible metal conduit, so we have what's called a supply side bonding jumper over from the hard pipe over to the actual enclosure. So fitting to fitting, if you will. This can be inside or this can be outside, okay? Most of the time when I see this application, it's installed outside, okay? So where it is installed outside, we want to keep in some things to remember. It says we're installed outside of the flexible conduit, the length of the bonding jumper, conductor, or equipment bonding jumper. However, I'm being referenced back to this area from the code, whether I'm dealing with equipment bonding jumpers. In this case, we're dealing with supply side bonding jumpers, by the way. And it says the limit is 6 feet, 250.102E2, and the size is in accordance with 250.102C, just like we've done before. So if I do need bonding jumpers, supply side bonding jumpers, or equipment bonding jumpers, I'm still going to utilize 250.102C. And if I'm doing it size for each individual raceway that I'm doing it, then I'm going to base it on the conductors within that individual raceway. Okay? So again, you have some options for your bonding. And this is an example. You can't see it on the screen if you're watching the podcast, but this is an example of a fitting that is on the end of an L that actually has a bonding lug on it, which would be utilized in this kind of fashion for, let's say, in this case, I believe it's liquid tight. And that's what it would look like, at least at the connector end. And then you would have another one at the transition end, okay? Because you cannot rely on it, depending on the size, you cannot rely on that FMC or LFMC, okay? Or even LFMC, okay? So that's what you would do for that. Now, bonding service equipment enclosures. Special rules are provided for bonding enclosures in the line side or supply side of a service disconnection mains. Thank goodness. All metallic enclosures that contain service conductors must be bonded together. We have to bond everything together on the service side, okay? We have this level of assurance that we have to maintain. Now, this equipment does not have overcurrent protection on the line side. Now, that's why we're doing all this, because we don't have any overcurrent protective devices that we control that can limit the amount of fault current. On the line side, we don't know what they're doing at the pole. You might know, I don't know, and I don't do their stuff, so I'm not worried about it. I'm following the code and hope that everything is going to work out if I follow the rules. So that's when we talk about 250.92, and we have to talk about what gets done there. Now, what does 250.92 tell us? It says bonding of equipment for services. It says the normally non-current carrying metal parts of equipment indicated in 250.92 A1 and A2, which we'll look at, shall be bonded together. So there is no question about it. It all has to be bonded together. So all raceways, cable trays, cable bus framework, that's the framework that supports and holds the cable bus, auxiliary gutters, service cable armor or sheathing that encloses, contains, or supports service conductors, except as permitted in 250.80. Now, that is an application where you have an elbow that maybe you have a metal race PVC in the ground for service conductors, and then you come to a metal elbow, and then you transition. Well, if that elbow's below 12 inches of dirt, that's really not practical for us to bond that. You get me? Yes, it's metal. Yes, it has service conductors, but it's 12 inches below the ground. It's not really practical for us to do that. We're not going to be running lines down into to bond those elbows. You with me? So that's what it's kind of talking about in there. You don't have to do that. But other than that, I still have to bond all the raceways together, whether it's an overhead coming down into a Myers hub in the top of a meter socket, all of that gets bonded together. Everything has to come together. Now, number 2, it says all enclosures that contain service conductors, including meter fittings, boxes, and the like that are interposed in the service raceway or armor. Now, interposed means if I'm going from the weatherhead on the side of a building and I'm using raceway and I'm coming down and I'm going into a meter, the meter is interposed in that service conductor that's coming down, right? It's being put right in the middle. It's still not service equipment. It's just a meter, but it's being interposed in that service raceway. So that's what interposed means, okay? So anything that's put in between where it terminates at the service disconnection means and the point of attachment, be it overhead or underground, those type of things, if they're metal, all have to be connected together and bonded, okay? All right, now bonding continues. So bonding at the service ensures that none of the equipment enclosures can become electrically isolated and become a shock hazard should a line to ground fault occur in that enclosure. We don't want any piece that could get energized that has no way for us to get that energy back to the source. So then it just sits there as a conductive medium, waiting for you to come along and touch it. And then when you touch it, if the conditions are right, you create that path to the earth. Now, for us, we cannot use the earth as an effective ground fault current path. It tells us that in 250.4. However, the utility company use it all the time because they drive ground rods at their poles at specific distances, and the voltages they use are so high, whereas our voltages are much lower, that they can achieve what they need to achieve with the earth being used as a path for return current. We can't do that. The impedance is too high for our system to do that, okay? And it only takes a little bit of Ohm's law and a 25 ohms for a ground rod to come up with that. You can find it very quickly. For example, in my scenario, I'm thinking ground rod, and I'm thinking 120 divided by 25 ohms is only 4.8 amps. Never going to trip a breaker. Now, in conversion to that, they're doing 13.8. 13.8 divided by 25 is 552 amps. That is going to blow their little 3, 4, 5, whatever amp fuse they have. So it works for them. It doesn't work for us, okay? We can't do that. That's why we can't use the earth. Okay, but what we're trying to do is not create any metal parts that is kind of just sitting there, isolated, waiting for you and me to come in contact with it. That's why we bond everything together. Now, it provides a low impedance path for fault current, so the fuse or circuit breaker on the supply side of the utility transformer will open and operate. So we're hoping that they did what they need to do, and they've got some fuses or circuit breakers or something there that we can have it transition from the secondary to the primary and actually on the supply side clear this. Let's hope. Okay. Now, the normally non-current carrying metal parts of service equipment required to be effectively bonded together include, as I said, service raceways, cables, cable bus, auxiliary gutters, service cables, armor, sheathing like MC or that type of thing. All that enclose, contain, or support service conductors all have to be bonded together. All enclosures, like service equipment, wireways on the supply side, all of that, meter fittings, meter boxes, all of that has to be tied together, okay? So we've established that. Now, let's give it a good example. So for those that are following along on the video stream, they'll see a picture on the screen that shows a meter from an overhead supply that comes down. And it comes into a meter enclosure, which is being interposed in the service raceway all the way through to the actual supply side and to the service disconnection means. Okay? Now, we follow the rules of what needs to be bonded together, and we did all that. Now, important note, 250.92b, all service bonding jumpers used around impaired connections such as reducing washers, oversized, concentric, or eccentric knockouts are sized as bonding jumpers per 250.102c1. So, if I've got any kind of impairment where my raceways come in, maybe it's knockouts, okay? Or maybe it's you knocked out too many. Maybe you need to do reducing washers. Anytime I'm involved in this, that's considered an impairment. And I'm going to have a bonding jumper. It's just no ifs, ands, or buts. Okay? Now, I cannot use standard lock nuts at all, except for mechanical. Means I can use it to secure the raceway to the enclosure, but that alone is not like what we can do on the load side for feeders and brand circuits where you can use it, except when we're over 250 volts. Okay, and we'll talk about that. But in this case here, I need to ensure that the reliability is here. So if I've got impairments of any kind, then I'm going to need bonding jumpers. And I'm not going to be able to use standard lock nuts to meet that need. Okay, now, some people ask me, okay, well, what if all the knockouts are gone, Paul, and it's the right size? Then can I use a lock nut, standard lock nut? And the answer is no. Now, you might not need a bonding jumper because you don't have impairments anymore, but you're going to have to use one of the other choices in the list that allow me to do this, like a bonding wedge, okay, or maybe even a bonding lock nut, which are not like standard lock nuts, but you can utilize that if you have the proper, you're not dealing with any impairment at all, okay? So you have options, okay? Just don't forget you do have some options. Now, we will go on, and so we can't use the standard lock nut, and I'm trying to see, so in the screen, I'm trying to show some examples for those that are doing the video. For those that are watching the stream, you'll notice that my main bonding jumper is in the panel, and you'll notice that I am bonding the metal raceway between the meter and the actual service disconnect enclosure, okay? And I'm bonding that, okay? And we have the main bonding jumper, and then you'll notice that I am doing a supply side bonding jumper over to the actual bushing that has an actual grounding lug, okay? And so that's just one way to do it here, because we're going to assume that I've got some impairments. That's knockouts, okay? So that's what I needed to do, all right? Now, the next one you'll notice is, because something else is important. That little raceway that's metal between the panel and the meter has to be bonded, but I only have to bond one end. I don't have to bond both ends. I only got to bond one end, okay? Because it's all tied back together that's going to get back to the grounded neutral. But I can do it at either end. So most people are going to do it in the equipment, the service equipment, not in the meter. But believe it or not, it is permitted to be done in the meter. Now, your utility might not like it. Some people argue that it's not accessible. It doesn't need to be accessible. Once it's terminated, it's done. What are you going to go in there? What do you need to get to it again for? What are you going to, how many of you ever gone out to the meter in your house and retorqued everything? Are you going to go out and cut that little link on there? Or are you going to call the power company and have it? Let's use a little common sense. Do it right, torque it, do everything right. I could do it in either location. Now, you might have a utility that says, I don't want it there. Okay. Well, they're the ones that we're getting power from, so we can't really argue with them a lot. So we're going to put it in the panel and make it easy on us. But we do have to bond at least one end of that raceway. Now, could we just make that PVC and forget all about that supply side bonding? Yes, we could. All right? We could make it very simple on ourselves and use more PVC than many people do use. Okay, I'm just saying. Now, let's talk a little bit about what I think is a beautiful thing, and that is 250-142. And this is the ability to use that grounded neutral conductor on the supply side to bond the metal parts. So in the picture, for those that are watching the podcast, you can't actually see it, but it shows a overhead coming down to a meter. And of course, the meter enclosure has a screw in it that is connecting the grounded neutral to the actual enclosure, so it's bonded. And now what we have is, and we're using nipples, metal nipples, it comes down into a wireway. And then out of that wireway, it goes out to two separate service disconnection means. And yes, they are grouped, they're in the same location, so everything is good. Now, in this case, since they used metal nipples between the meter and between each one of the main service disconnects to the wireway, I have to bond at least one end of that nipple. So in this case, I'm going to use it. Now, again, this is if I've got impairments, okay? If I've got impairments. Now, if I punch these and they're the perfect size, then I can use a bonding type lock nut with a screw that drives into it, or maybe even a bonding wedge. I mean, I have other options to use, okay? But if it's an impairment, then I'm going to put a bonding jumper. So in our case here, we're going to say that we encountered some concentric knockouts. Okay, well, in that case, we're going to bond one end of that raceway, and we're going to ensure that it's bonded, connected to the grounded conductor. So we're going to put supply side bonding jumpers on it. Now, how do we size those? They're sized based on the conductors that are in that raceway. that we're bonding. That's how we do it. And we're going to size it based on the ungrounded conductors. We take the largest ungrounded conductor. No, we don't add up all the phases. We just take one of the phases and we utilize it. Now, all the phases are the same size. So again, we're just going to pick one of them and utilize it. And then we're going to go to 250-102C and we're going to pick the size of that supply side bonding jumper. But what's important for me and you is the fact that I do get to utilize the grounded neutral conductor under 250.142 in this application. And it means that I can ground my meter. It means I can ground my metal wireway, all of that on the supply side. Now, interesting enough, we have some changes that are coming in the 2020 code that also tell me that I can treat all of my disconnects and everything that's allowed to be on the supply side of the service under 230.82 to treat it just like you would a service. And so most of those, even though they're not services, like for PV systems, wind generation, or whatever, but if I'm going to bond them, then guess what? I'm probably going to use the allowances here, and 250.24 is going to ultimately tell me that I can use 250.142 and use the grounded neutral conductor to make that bond, and I'd be okay. All right? So again, you see how things are working and tying everything together. Again, it's on the supply side of the service disconnection means. And here you see we have main bonding jumpers in both of our panels, okay? Now, methods of bonding at service equipment. Again, we have various methods to do this. Bonding requirements are more restrictive at services than they are downstream from services for feeders and branch circuits, obviously. Service equipment and enclosures can be subject to heavy fault current that are an event on the line to ground faults on the supply side. We have to hope we can trip a fuse upstream. We don't get to control that, okay? We hope that they've got what they have on the utility side. We just need to bond everything together. On the load side, we have those overcurrent devices that can protect us. We don't have it on the line side, okay? So that's a problem. And we're hoping that we can control those overcurrent devices at the utility. Let's hope. So what are the methods that we can do at the service? Now, 250.92b says bonding jumpers meeting the requirements of this article shall be used around impaired connections. So this is what's driving me to use bonding jumpers, such as reducing washers or oversized concentric or eccentric knockouts. It reminds us that standard lock nuts or bushings, standard bushings, shall not be the only means for bonding required by this section, but shall be permitted to be installed to make a mechanical connection. You know, connect that raceway to the box, connect that fitting to the box. That is a mechanical. That is okay. But we cannot rely on it if we have some type of impaired connection. We're going to need a bonding jumper. Now, it goes on to say, electrical continuity of service equipment, service raceways, and service conductors enclosed shall be ensured by one of the following means. Number one, bonding equipment to the grounded service conductor in a manner provided in 250.8, which we could have probably put in here, bonding the equipment to the grounded service conductor in accordance with 250.142 in a manner provided by 250.8. That probably been better language. It also gives us and says, well, you know what? If you've got these raceways that have service conductors in it, connections utilizing threaded couplings or threaded hubs on enclosures if made up wrench tight are okay. So in our meter, we had that hub in the top. So I come into the top and it threads into it, and that hub is connected to the enclosure, usually with 4 screws. It's okay. It's considered bonding. That raceway that has service conductors in it are now bonded to the electrical enclosure, or in this case, say the meter. They are bonded together. And I can use that hub to do that because it's a threaded connection. Also, if it goes up to a weatherhead and I've got 2 sections of rigid, let's say, that coupling that connects them to the 2 pieces of pipe together, that is okay. That is making the connection, and that is adequate to continue that bond between the 2 raceways that contain service conductors. Perfectly okay, as long as it's made up wrench tight, okay? Third is threadless couplings and connectors if made up tight for metal raceways and metal-clad cables. So I have the ability to utilize threadless couplings and connectors if they're made up right, okay, and they're tight for metal raceways, and metal-clad cable connectors can be utilized for this application. So they have to be right, and of course, with metal-clad cable, the connectors, obviously everything has to be listed. So again, all of that taken I'm okay with threadless couplings, okay, and connectors if made up tight for metal raceways. Another example would be, this is kind of like where you have two raceways that come together with a compression fitting. Okay, that is threadless coupling. So again, you have options here. And then of course, number 4 says other listed devices such as bonding type lock nuts, bushings, or bushings with bonding jumpers. Okay, so I have options. We just have to remember, most importantly, not to use standard lock nuts for anything other than mechanical. And if I've got impairments, I've got to have bonding jumpers. And we know how to size those bonding jumpers because we've been doing it a couple times now. Now, methods of bonding at the service continued. Service conductors only have short circuit protection. Okay, remember that. When the circuits come in, from the utility, from the transformer, and they come in, they are on the supply side of the overcurrent protected device. They don't have ground fault protection, okay? And they don't have, now, so in this case, also remember that they also have overload protection to a point on the load side, okay? So service conductors only have short circuit protection provided by the overcurrent device on the line side of the utility. So that only provides short circuit protection out at the utility. Now, only overload protection is provided at the load end of the service conductors by the service main overcurrent protection. So again, make sure I made that clear. On the utility side, short circuit protection, that's not really going to give any overload protection because it's typically on the line side of the utility transformer anyway, and we're getting it from the secondary side of that transformer. So it's got short circuit protection, but the only thing that those service conductors from the secondary utility to our service disconnect or the main breaker, it only has overload. It does not have short circuit or ground fault protection. That's going to be on the load side of your service disconnect mean, but not on the line side. So it's only overload. And how is that true? Because if it's a 200 amp main breaker, it's going to limit the current to 200 amps. It's not going to allow it to overload. You with me? Okay. But that's the only protection that it has. That's it. Now, one reason the code limits the length of service conductors, and you're probably all familiar with this when it comes in 230.70A1, it says outside or nearest point of entry. That's the reason, because these conductors don't have any short circuit or ground fault protection. They're not going to clear a breaker in our sense of the world. All right? So they only have overload protection. So we don't want these conductors that are theoretically really unprotected running through the building. So people ask me what my interpretation of outside or the nearest point of entry is. Literally, the moment that it pokes through the wall is the nearest point of entry. That's how I look at that rule. Okay. All right, so now you see some examples. So here's a standard lock nut for those that are watching on the video. For those that are on the podcast, you can't see it, but I have a picture of what's called a bonding lock nut next to a standard lock nut. And there is a significant difference. Obviously, it's like night and day. It has a screw that is going to drive down into the actual raceway, okay? And that's going to bond everything together and lock it in place, all right? So that's the bonding lock nut, and I show it right next to a standard lock nut, okay? Now, when can I do this, a bonding lock nut? When I don't have any knockouts that are concentric or eccentric or impairments, then I could use these. So if you plug a hole, it's perfect. You can use one of these on the supply side. It's perfectly fine. Just can't use a standard lock nut. Now, what about bonding wedges? All right, well, now bonding wedges are used around concentric eccentrics or oversized openings encountered, and you can use them with or without a bonding jumper because in many cases, if you have a total, everything's knocked out, then you could put this on and then put the standard lock nut on it and drive that screw into the raceway, and then it would bond, it would tie everything together, and it would be perfectly fine. However, I could also use a bonding wedge if I needed to have a bonding jumper, because usually they have the ability to add a lug on them. Just make sure you check with the manufacturer to make sure. But it has a lug on there so that I can put my supply side bonding jumper to it if necessary. So they're very versatile, okay? Now, when we talk about the threadless couplings and connectors, those that are watching in the stream, you see a picture of a EMT raceway And again, these threadless for different types of raceways are all acceptable. We already saw that. The conduit hubs, a picture of one's on the screen. This would be an example of what you see coming into the top of a meter enclosure. It could also come into the top of a NEMA 3R, for example, if it's outside. I see that very common as well. Okay, so that is okay, and that takes the raceway that's threaded into that hub to the actual equipment that it's connected to and bonds them together, and that's perfectly okay. And of course, you have the threaded couplings and bosses and everything, again, threaded raceways like RMC, IMC, and what have you, all connected together. And this is an example where somebody's coming in. You can't see it in the podcast, but this is an example of what the hub looks like on top of, I would assume, a NEMA 3R enclosure, okay? And it mating the two together. And we give another close-up view of what it looks like, okay? And again, we have a picture on the screen that actually shows the bonding of one side of the metal nipple or raceway connecting two pieces of equipment. We see the bonding jumper that it's applied to the bonding bushing that's installed, okay? And again, I'm showing a picture of a bonding bushing. And this one is specifically designed a specific way that it actually locks down on the actual raceway. All right. Now, talk about methods of bonding when we talked about 250.92b. And we have all these different methods. So we got listed lugs, pressure connectors, other listed means, and 250.8, because that's what it alluded to. All, again, connected to the ground and neutral conductor if we want. Threaded couplings, threadless. We have a bunch of lists of everything. Remember, standard lock nuts are not permitted for bonding by this section. And bonding jumpers are required when we encounter impairments like concentric, eccentric, damaged. I see this too. Damaged knockouts. Again, it makes you realize the importance of it, that you have to make sure that you're actually ensuring the reliability of that connection. Very important, okay? Now, let's talk a little bit about bonding at the remote meter. So this is interesting. So all metal equipment containing service conductors are required to be bonded together. We've already established that, and it has to be connected to the grounded service conductor. We know this. We've read it in 250.92a, and we're coming close to the end, so hang with me. This includes remote from the service equipment meter cabinets and meter socket enclosures, even current transformers, CT cabinets, raceways, and auxiliary gutters. They still contain service conductors. Still all has to be bonded together. Now, the grounding and bonding of equipment to the grounded service conductor at locations on the line side of and remote from the service disconnect means actually increases safety by making sure you bond there. Now, you might say to yourself, well, if I bond there, can I bond again at the service equipment? Absolutely. But you can do it at multiple locations. Again, it's all on the supply side. It is all good. Okay, so let's look at an example. Now, remote equipment should never be grounded only to the grounding electrodes, such as a ground rod. You've heard me talk about that. You can't just drop it. That's not what you should do. That remote equipment needs to be connected to the grounded neutral conductor, okay? Never just to a ground rod, just driving ground rods out there. That's not what we're doing here, okay? And so if a ground fault occurs on the line side of remote equipment and not bonded as required, you didn't do it properly, only means for cleaning ground faults would be through the grounding electrode and the earth is high impedance path. This is the same example we gave with the post in a parking lot. If you try to use the earth, it's just not going to happen. So even at that remote meter, you want to make a connection to the grounded conductor because the neutral, because if you were to just take a connection to the earth and think that's going to work, it's not going to work. Not going to happen. Okay. Now, no overcurrent device will operate or open, leaving the equipment enclosed, will leave the equipment enclosure at a dangerous voltage to ground potential. Okay. It increases the potential between the two, and we know that current flows from potential to potential. It becomes a hazard, okay? Now, any person or animal that comes in contact with the enclosure can be shocked or electrocuted. So let me give you an example here. So those that are watching the stream, I have a CT cabinet, and it is 100 feet away from the service equipment. And I love this graphic. For those that are in a podcast, you can't see it. this is a classic example of the piece of equipment that is no longer going to be allowed in the 2020 National Electrical Code. I can't have a single enclosure with 6 disconnects in it, okay? And if you don't know what I'm talking about, go listen to my video or podcast that talks about the changes to the 2020 code, and you'll see what I'm talking about. But in this case, it's 2017 code, it's permitted. So there's 100 feet difference between the two. Well, you notice at the CT cabinet, we've got, obviously, for those that are watching the video, we have raceways coming in from the bottom. Obviously, we're not encountering any obstructions. Any impaired knockouts or anything like that. They're just simply cut holes. Why do we know this? Because you see on my graphic that I'm using a bonding type lock nut to make that connection, okay, to the enclosure. Now, this metal enclosure, the CT cabinet, you see here that it is bonded to the neutral. So now this enclosure is bonded, right? Okay, now, once we do that, and again, it's not required out here at the remote to go to the grounding electrode, but you can. It's permitted to do that. You can if you want to. It's not going to matter. Again, remember, the connection to earth is for lightning, transients, and high power lines that could come in contact with lower power lines. It's not to clear any devices or anything like that. It's okay. I can permit it to do it there if I want. Now, you might get some utilities that say, nope, you're not going to do it. Okay, don't push it. I'm fine. Now, that same utility is probably not going to let you also bond this raceway. Remember, you can do it at either end. They're not going to let you do it inside the CT probably either. So, okay, no problem. So we're going to do everything at our service equipment. So once we get 100 feet to our service equipment, then, and only then, we get to bond the raceway that connects the CT to the service equipment. So we have to have what's called a supply side bonding jumper. How do we size that? Based on the conductors that are supplying this service equipment. In this case, in our graphic, and those on the podcast can't see it, but it is 2 sets. And let's say it was 2 sets of 500 kc mil. So I have black, red, blue. Now, of course, I'm going to get a lot of people that tell me, Paul, your colors are mixed up on your service equipment. But to be honest with you, I do that a lot of times on purpose because nothing tells me that A needs to be black, red, and blue. Okay. But typically, would I install it black, red, blue? Yes. Okay. Typically, I would. But a lot of times, I like to shake things up and cause problems. You know how I am. So anyway, so in this case right here, let's focus on what we're here for. This is our service equipment. This is our neutral terminal bus. These are where our neutral conductors come. Here's where our main bonding jumper is. It's connecting those neutral conductors to the metal enclosure. And we're taking our grounding electrode system, whether it's ground rods, ground ring, whatever it may be, up to this common location. So they're all tied together. So we're sizing that supply side bonding jumper up to that. In this case, it's not a nipple because it's 100 feet. What are we sizing at? We're going to 250.102C1. And since they're all in one raceway, we're using C1, literally. And this is going to be, let's just take phase A. And that is 500 and 500. That's 1,000 kc mil. And then we're going to go to our table and we're going to size that main bonding jumper based on 500 kc mil. In this case right here, we're going to size it based on 1,000 kc mil because it was 2 500s. Excuse me there. Okay. Now, if this had been parallel raceways, then we would have done it in accordance with 250.102C2, just like we did earlier. It's not brain surgery. Okay. Pretty simple concepts that we're dealing with here. Now, what about the remote meter that's typical for residential? And that is where I have, and this is what I used to do. I had a meter that was remote from the house, and I had the overhead would come down into the meter, and in the meter, it would go from the meter underground and then over to the dwelling. Okay, well, again, remember the principles. All metal raceways and non-current metal parts shall be bonded together to the system's grounded neutral conductor within the enclosure. So that's why typical meters like this, the neutral actually bonds to the enclosure. Number 2, all bonding in accordance with section 250.92B1 for bonding at the service. We have to do that at the service, but remember, we're going to do the same principles here. Okay, so if it is an impairment, we're going to have bonding jumpers. In this case, in our graphic, we had a perfectly sized knockout. So we used a bonding lock nut, which you might not be able to see, those that are watching the video, but there's a green screw in there, and it does make that connection. Okay. Now here, I'm showing a ground rod shown in the graphic. It's permitted to me to do it here. It's not required, but it's permitted. I can do it here. All right. They might not like you to do it, okay? But, you know, you can if you want to. Now, bonding a multiple service disconnection means, so when I'm installing multiple services that are permitted by 230.2a through D, and so I've got multiple services at a building and the code permitted it, installation of service that have multiple disconnect means can take several forms. Now, let's keep it simple. The basic rules for sizing the supply side bonding jumper for bonding these various configurations are still found in 258.102c. Just like before, don't get confused by the number. Same concept. The supply side bonding jumper is on the line side of each service, and the main bonding jumper is still sized based on table 250.102c1. Relax, you're not doing anything different just because you got multiple services here. The size of the supply side bonding jumper for each raceway is based on the size of the service entry conductors in that raceway. Okay, so this is what we're talking about. For those that can see this on the stream, I've got a CT cabinet. It's coming in. And I've got the metal raceways everywhere and metal enclosures. And I've got parallels coming down. And I got two services coming down here. Okay, two drops. Okay, because I've got multiple service disconnects here. All right, and so it's paralleling down, and it's paralleling down into two raceways basically. So I've got a black, red, and a white in one raceway, and a black, red, white in the other. And of course, at the top of the weatherhead, they probably one drop from a pole. Okay, so it's still one service, but it splits up, and I have two separate raceways that are coming down. Okay, now all of the bonding that we have to do is in all these metal raceways. So let's kind of look over this. For those that are watching the video, this is going to be really neat for you. For those that are in a podcast, it's really going to be hard because I've got a CT cabinet. I've got two service drops coming down in raceways, and then it's going from the CT into a wireway with also two separate nipples. And then from that wireway, it's popping up into three separate panels. Okay. Each one of these have a main disconnect. Each of these are meeting the 6 disconnect rule. Right now, there's only 3, but I could have 6. I could have had a longer wireway, and I could have had 6 there. You with me? Perfectly fine. So the conductors that are coming down in each one of these, the drops that are coming down from the point of attachment, I am basing the size of that supply side bonding jumper based on the size of the conductors that are in that raceway. And I have another one right beside it. I'm sizing that one as well on the size of the conductors in that raceway. Now, could I have run one and looped it through them? Absolutely. They're just treated as in parallel. But I chose to do individuals because maybe I'm worried about the limitations on my lugs. Okay, we're going to guess. All right, so now I go through the CT cabinet. The CT cabinet is utilizing the allowance in 251.42. It's bonding to the neutral conductor, so that enclosure is bonded too. Everything's done. The easiest way to remember bonding is to take it piece by piece by piece by piece as you move through the system. So now I go down, and now the two parallels are leaving the CT cabinet, and now they're going into the wireway. Okay, so I have a black, white, and a red in one nipple. We'll say a nipple. And then I have black, white, and red in another one. So now I have to bond those raceways based on the individual conductors that are in that raceway. So I'm going to take whatever the size these would be, and I'm going to 250.102c1 and size that supply side bonding jumper. Remember, we're still on the supply side here. And I do the same for this other raceway. They're identical to the ones that we had that were coming into the CT from the service. So again, we don't have to do more work than necessary. They're the same conductors. It's the same application. Now, here's the thing. Now I need to bond that metal box. Now, in our case, we're using a bonding jumper that is supplied with the actual wireway. Now, if it wasn't, and we're using a lug that's provided by 250.8 and connecting it over to a bus, we have to size now that main bonding jumper. Okay? Or excuse me, we have to size that supply side bonding jumper for that wireway. Well, we have to size that based on what? The two that are supplying it. So if these were 500 kc mills in each raceway coming in, then that jumper, supply side bonding jumper that we're doing here for this wireway is going to be sized based on those two raceways as if we're doing them in parallel. So 500 and 500, that is 1,000 kc mil. Then I'm going to go and size it. Now, could we make our world easier? Could we just take that lug and mount it to the metal box that the grounded neutral conductor is connected to and not have to size anything? Yes, if that's how it works out and that's how you buy it and it has the ability to connect it to the actual wireway, then you're good to go. But if I have to size a main bonding jumper of the wire type, just remember we're going to treat both of those that are coming in and size it for that. Now, we sized each raceway nipple because we only had to worry about the conductors that were in it. Once we're in this wireway, we have to worry about both of those, okay? Now, why didn't we do that over the CT? Because the CT, we used the neutral conductor, and we put the green screw, we bonded it straight to it, okay? That's configured into, that's built into the CT, but not over in the wireway. So just remember, if we got a lug to a bus that has the neutrals, and you're going to connect them together, then you have to size that supply side bonding jumper based on the two sets that are coming into that wireway, okay? If it's built into it, then it's factory supplied or whatever, then you're good to go. You don't have to do anything. Now, that same location is where we're also now going to bond the nipples that go out to each one of our service equipment enclosures. Now, you could say, couldn't you do it from the other end? Sure, I can do it from either end if I want. But this is a perfect place to do it because this is inside of the actual wireway. There's a lot more room to do what I need to do here. So I'm going to size it. Now, how do I size those supply side bonding jumpers? You guessed it. It's based on the size of the conductors that are in those individual raceways. And that's how you would size it. Okay? And each one of those conductors in our example are going to be different sizes because the overcurrent devices, the service disconnect and all the rating is different for each one of these. One is 300 amps, one is 200 amps, and one is 125 amps. So the supply side bonding jumper for these will be different size for each one because the conductors will be different sized for each service enclosure. Okay, so let's kind of do it. We've done it here, and so let's kind of work it out. What is the size of the supply side bonding jumper in that illustration that we just looked at? So we're looking at A. And there's your answers. 1 aught would be what you would use for all the A's. So all of these A's would be 1 aught. The B, which is dealing with 1,000 kc mil, remember, because this is dealing with 2 of them. So if this is the wire type, we're sizing it based on these as if they're parallel. Okay. So that would be 500 and 500. It's 1,000. Okay, and that's what resulted in a 2 aught. Remember, all this in 250-102C1. Then the next is the C. Now, the C was dealing with a 300 kc mil for this 300 amp device. So this is 300 kc mil. So we go to 250-102C1, look at 300 kc mil. It says it needs to be a 2. So that is what our supply side bonding jumper will be for that nipple. The next one was a 200 amp. And so if you do that, the 200 amp needs a 3 aught copper. So that would be 3 aught. You go to 250-102C1, and that's going to require a 4 gauge for the supply side bonding jumper. And then the last one was 125 amp service. And so, again, that would be a 2 gauge for that. And again, we're getting these ampacities based on 310-15 B17, by the way. And B16, excuse me, not 17, 16. Woo! All right. Now, that's how we size all those bonding jumpers. And that is about all that we're going to talk about tonight. Okay? So, hopefully you got something out of that and it was important for you. So, I'm going to end the stream. Over for us that are listening over on the podcast, I want to thank y'all for listening to another episode. Hopefully I conveyed it as good as I could for you folks. And for those that are in the actual video, I'll hang around a few minutes to answer a few questions, and then we'll end tonight's episode. So hang on the video stream. All you that listen to our podcast, thank you. God bless. Until next time, stay safe. You've been listening to Electrician Live with your host, Paul Abernathy. All right, guys. All right, so I'm back in the video stream. Hopefully the stream went okay. And that's a lot of information for an episode. Wow. And so if you have any questions, you do not need to bond at both ends, Elwood, on those nipples. Only one end. Why would you do both ends? We're only trying to keep the nipple from being energized. By bonding it and taking it back to the grounded neutral conductor as we're required, that's going to allow that energy that would get on it back to the neutral, which can get back to the source. Why would you do it at both ends? It's not needed. And the code doesn't require you to do it at both ends. I only have to bond the nipple. I can do it at either end I want. So nope, you don't have to bond it at both ends. In fact, if you can prove to me that you have to bond it at both ends, I'll give you $1,000 cash. Prove it. I serve on that code panel, so I can tell you you don't need to do both ends if you're talking about a nipple. Kevin says, never use ground rods at lightning poles. You should have been in here last night, Kevin. I don't have a problem with them as long as it's not connected to the grounded conductor. It's only to the metal shell of it. If they want it for lightning and whatever, engineers designed it that way, that's fine. Just don't rely on it to do anything. That's all I care about for that. Let's see here. What do we got here? Let me see if we got any other questions. Good evening, everybody. Thanks for coming. I don't have any questions that I see in here. And I assume the stream's still going. It was a good stream, I hope. Any other questions that anybody has? I'll be more than happy to answer any questions that you might have that related. It looks like I did not drop any frames, so I assume the stream went pretty good. I don't see any problems with it. So again, if I have no questions on the grounding and bonding for services, hopefully you got something out of that, folks. It's a lot of information, but it's critical information. Okay. So Ron says on the lightning poles, aren't they grounded anyway, like the concrete pillars? I think you're totally confusing what we were talking about, Ronbo. We're talking about pole lights or lights at parking lots, driving ground rods for them. That's what we're talking about. That's what it doesn't do any good to do that. But you can, if it's going to get lightning and it can dissipate it to the earth, some people think that it will keep the base of the concrete base without cracking or anything like that. Then they want to do that. That's fine. But don't think that it is actually there to facilitate the operation of an overcurrent device. It's not. And we did that last night. I am not getting into that debate again. I am not wrong and whatever. Let's see. I was told by many that Article 250 is one of the most important, if not the most important article in the code. I have a question about a lightning issue I had in the field. It is to me probably one of the most important because it's so safety driven. Right? If you don't do it right, so many things can go wrong. And if you don't bond things correctly, things can get energized. You know, the funny thing about electricity is that even when people do it wrong, it all seems to work. That's probably the beauty of it. Even when a jackleg does something, it still runs and they pat themselves on the back. But what happens when the owner of the premise comes in contact with somebody else's ignorance? Then that's where we have accidents. So again, I spend a lot of time talking about grounding and bonding. And it's one subject that I actually co-wrote a book with a friend of mine, Phil Simmons, on. And I am very passionate about grounding and bonding. And I spend a lot of time involved in it. And so, you know, if I tell you something about grounding and bonding, it's probably accurate because I've spent a lot of time invested in it. Let's see here. Would it be safe to use a non-metallic nipples to eliminate bonding jumpers? Sure. It's not safe. If you're using the raceway, you can use nipples, and one of my graphics showed that's perfectly fine. You just don't have to bond the nipples, right? Do you have classes that someone can take? Because I'm going for my Nick. We have the fast tracks programs, and some of my fast track students are in here. They can tell you it's definitively, to me, the best exam prep software, interactive quizzes, and you interact with me because I grade your reports. I don't think there's any of them better out there that can prepare you for an exam. And to find out more about that, or even to look at some demos that I have, go to masterthenec.com. And you'll see courses. Click on courses, or you'll actually on the front now, I think we redesigned it. There's quick links to the Fast Tracks programs, and you can read about it, and there is no better course out there. Go watch one of our demos, or better yet, come in here Wednesdays when we do a Fast Tracks demo, and I can show you how it works. But again, we have videos that show all that as well. I don't think there's any better structured exam prep program out there. Of course, it's not just for exam prep. It's for anybody who wants to learn the National Electrical Code at a higher level, but it's been developed and kind of added to and nurtured to be a very definitive success rate for exam preparation. Okay? It's not just reading books. It's not just watching DVDs. It's interactive, and it's got examples of calculations you have to perform, and you have competency reviews, you have section questions, you have end of unit questions, you have practice exams, you have final exams, you have over 1,200 questions that are engulfed in the program. Check it out. Okay, let me see here. Raymond, Lightning, sorry, I installed a controller receptacle in a junction box and the lighting in one of the buildings. I'm not sure I grabbed that, Raymond, but another thing to say is there's a reason why the code is started to move. Now, there's a reason why surge protective devices are in the code. Now, in the 2017 code, it's 280 and 285. In the 2020 code, it's 242. For 1 and 2 family dwellings, surge protection is going to be required now at the service, not just because we're worried about lightning. I mean, we are worried about lightning. We are worried about lightning. But we're worried about the effects of lightning. You know what I'm saying? And the effects of lightning can tear out and cause a lot of problems inside of a dwelling. But you know what? It's not just in a dwelling. So look for this to expand and change. Already required to have SPDs on a lot of systems as well. Even emergency systems have SPDs, right? But I look for it to expand even more. And the reason is we have so much sensitive electronic equipment. But for me and you, we have to make sure that we separate the lightning issues from the grounding and bonding issues. While they do come together because of the electrodes and everything we're doing, they are vastly different. They just converge. I'm more concerned, to me, about the importance of equipment grounding conductors, supply side bonding jumpers, equipment bonding jumpers, sizing everything properly, following the code, making it electrically safe. We're already required to put grounding electrode systems on buildings anyway, so if we just follow the code, that's pretty cut and dry. I mean, you know what? We can have everyday helpers run a grounding electrode conductor from the panel's grounded terminal bus to an electrode without being too much brain surgery. Okay? But how many mistakes get made sizing equipment grounding conductors or terminating them right, or supply side bonding jumpers, or main bonding jumpers, or system bonding jumpers, or supply side? That is where people can go funky. And that is all tied directly to safety, because you got to remember, we're putting conductors with current on it, or voltage that is resulting in current based on the loads that are tied to it, that are always there ready for us to come in contact with in our walls. I mean, I can kill you with 1/10 of an amp. I don't need 50,000 volts and 50,000 amps to make your eyes pop out to electrocute you. We can do it with 1/10 of an amp. If I bond you right, if I ground you right, if I do it right, we can do that. So if you've ever been shocked and you're still here to talk with me, then you know what? You obviously weren't electrocuted because you're here. And secondly, you're daggone lucky because you can get killed from any 15 amp. That's why I say electricity, being an electrician, is a heck of a lot of responsibility. Heck of a lot of responsibility. That's why I love this trade. We are the givers of light. We are the ones that make things safe. If you see somebody doing something wrong and you're afraid you're going to hurt their feelings, don't. Because the life they may save might be somebody you love by doing it right. You with me? God, I had to get off that soapbox. Ooh, I got off of it. All right, what does the brand of the service affect how it is bonded? No. You mean when you say brand, not really. I mean, every manufacturer might have their own way. One might supply the green main bonding jumpers. Another one might do a Z strap, screw. One might screw. One might do the strap, Every manufacturer is a little different, but they all have to have their equipment evaluated, right? All has to be evaluated, okay? So they're all going to have a main bonding jumper. Some might have screw, some might have a strap, but they're all going to serve the same intent, okay? The electrons that we're dealing with don't care either way, They're just trying to get back to the source, which they don't really do that, but it's easy for us to explain it. I love that analogy. Electricity is like the flow of water, like a Bruce Lee thing, wax of water. The reality is that's really not how electricity flows, but it's so much easier for us to explain it that way, right? Just so much easier to do that. Let's see. How would you bond an existing swimming pool? Wow, outside of this topic. Well, outside of this topic, but I knew you were just ready for a question. How does your bond an existing swimming pool that is being remodeled? What are some of the requirements needed to be bonded? Well, that's going to be in 680.26, and I can't really go into that. Again, I've been doing this now for 2 hours. I'm not going to get into 680.26, which is the requirements for bonding around swimming pools. That's called an equipotential bonding grid. But go look at 680.26 and you'll get it. But I also remind people that I have an 8 or 7 part series. Maybe 7. I have a 7-part series on swimming pools up in my YouTube channel. You just have to go to the archives, which is the top right, click on it, because usually it loads all the new stuff. But you need to go look at the old stuff because I've got swimming pool. And I've made it a little easier. Now, if you go in the playlists, they're in the playlists. So you ought to see one for NEC. Go in the playlist and you'll see my swimming pool stuff. And that's basically like me talking here. You can go watch that. And that will tell you everything that you need to know about swimming pools, I promise you. Let's see here. Let's see. Do you need a bonding bushing if it is 120-208? Doesn't change the fact. If it's service conductors and it's coming in, if it's bonding bushings, the bonding bushing in its sense, you got to remember what we're saying here. You have a bonding bushing, okay, which you might utilize, but again, we have to remember if it's service conductors, if it's concentric, eccentric, or any kind of impairment, we need a bonding bushing with a bonding jumper. You with me? Now, could I use a bonding bushing on those raceways that come into an open bottom? Sure. It's not mechanically connecting to anything. So I have a bonding bushing with a bonding lug, and then I have a supply-side bonding jumper leading over to the ground and neutral terminal bus. Yes, then I can use a bonding bushing for that. Okay? But at 120-208 doesn't change it on the service. It's still service conductors. Still have to follow the rules in 250.92 for that. Cool. Rombo says, cool, I need the swimming pool info myself. Thanks for the help there. Yep. Nick, Ron, I did read your email. Sorry, I've been so swamped today. And it's like a freaking sauna in the studio, my office area that I do this all in. And the best I could to get one video up to Patreon today because of all the crap that's going on here. So I apologize. I will get back to you, brother. I promise that I will. But yes, go watch that swimming pool series. Now, one thing you will notice that the quality of my videos have totally dramatically changed over the last couple of years. Now, I've been doing videos since 2004. So we've gotten a little bit better. And hopefully the stream the stream is a little better now. Hopefully you noticed that I have all the software in place. My lighting is all new, coming. It's not here yet. And hopefully my lips aren't looking like I'm wearing lipstick tonight. But anyway, here's the thing, guys. We have so many videos and podcasts. Look, if you've never really bit into the podcast stuff, I encourage you to get into it. I actually listen to podcasts at night before I go to bed. I have what's called a Alexa, and I have it near the bed, the nightstand. And I listen to Spotify and I listen to podcasts on that. And I just tell it to shut off after an hour because I'm probably going to fall asleep. And then it literally will play it and then it shuts it off after an hour and I go to sleep. I listen when I'm in the shower. I listen to all kinds of podcasts. It's interesting. There are literally, I think it was, I can't remember. There was something like 750 million YouTubers, but only like 700 or whatever thousand podcasters. If you think about that aspect of it, talk about podcasting is such an opportunity. It's such a platform. I listen to in the car. I have people that listen to our podcasts on their job site. They pump it on the job site to all their employees. It's pretty cool. And it sent me a video of them jamming. And anyway, I don't know how you jammed to me, but they were listening and anything. So anyway, let's see here. Any other questions before we cut this out? Raymond says, I watched a video earlier about paint that glows and is dimmable with a low current. Is something like that available here in the U.S.? I have no idea, but it's probably what we're talking about is luminescent paint. And there is an allowance in that in high-rise buildings for markings of exits and things like that. I don't know about the dimming of it, but it's luminescent. But I'm sure yours must be a paint that it's actually conductive. I've actually saw a little video on YouTube about that, but I'm not aware of any of that, and it hasn't made it into the code, obviously. But again, I'm not aware of it, of that, sorry. Okay, that's it, guys. I am tired. It's been a long, long day. I want to thank everybody out there for your continued support. I want to thank everybody out there who subscribes to our streams, who comes during the week, who's joined our Fast Tracks programs. Incidentally, I should make an announcement. The 2020 series of our residential book, which is an amazing book, by the way, it covers everything residential. I mean, room by room by room. Our commercial electrician commercial on the 2020 is available. That's an amazing program. Teach your blueprint reading. Even comes with the blueprints, so you get used to all that stuff. The grounding and bonding is available in the 2020 edition. We have a program that's out on that's already on our website, masterthenec.com. And I'm excited to say this, and I'm going to say it now, and many of you are not going to need it, but the 2020 edition of the Fast Tracks program, and again, most states aren't going to test on that for at least another year, which would be outside of the scope of what you're doing now, because most people are going to use the 2017 edition. But for those that are interested in getting a kickstart into the 2020 code, for example, the Fast Tracks will be available on May 25th. That deserves something. Hold on, guys. Hold on. Here we go. I mean, that's all it gets. It's available on the 25th, but we are taking pre-orders now for that program. Now, that one will be $335 for a year's access. However, I am freezing the price on a pre-order. Means the reason is my LMS fee went up $20. So if you purchase that program from now until the 22nd of May, you can get it at the same price as our 2017 program. Okay? For all those that might be interested in that for the 2020. I've had people that were interested in it. Again, it's all based on what you're going to be testing on. However, we do have a large amount of people that are in our Fast Tracks programs that are not preparing for exams. They just want to learn the code better. Okay? So, and with that launch, our CMECP program is also going to be bumped to the 2020 edition. So that's exciting news too. So anyway, those are going to be available. So you can pre-order them now and get it at the same price as the 2017 before the price goes up on the 25th. Okay? Just wanted to make that announcement in case anybody was interested in that or you knew somebody that was interested in that. Okay? Again, you might not need it to prepare for an exam, but some people want it because they need to get up to date on the 2020. Also, you could join our Patreon, and we cover the 2020 article by article, slowly and methodically. That's a commitment that you have to make every month, but that's a commitment for me because I have to produce videos for years because it's going to take a while to get through the NEC. Trust me. I've done this before, and it took me over a year and a half to do this. Yes, I have covered the entire NEC before. Back in the 2005 edition, I covered the entire NEC, and it took me about a year and a half to methodically go through it. Well, I started that mission again for the 2020, and that's over on our Patreon. So we appreciate all you that support us on Patreon. All right, so that's it, folks. Thank you all. God bless. Take care. Be safe. Enjoy. Hug your family. You never know when tomorrow will bring. It can bring happiness or it could bring temporary sadness, but we all can recover. Till next time, folks, stay safe. And again, God bless. You've been listening to Electrician Live with your host, Paul